let's look at exponential functions, what they're used for, and how we can represent them both graphically and using an equation. First, let's look at these two series, A and B. Series A and B both give you a few pieces of information. Number one, they both describe what's happening over a course of time. In this case, there are 5 different units of time or cycles. If you can imagine them simply as an hour, 2 hours, 3 hours, 4 hours, 5 hours, or simply 1 cycle, 2 cycle, 3 cycle, 4 cycles, and 5 cycles. It really depends on the problem and what the problem is actually measuring. As we look at Series A and B, we can very quickly see that Series A happens by adding 2 each time. Every time we add 2, we increase the number of dots and we create the next cycle. So Series A grows very straightforward. Series B grows in a slightly different pattern. It starts off with that same plus 2, but we can quickly see as we move from 2 to 3 that adding 2 stops working. So we can go ahead and cross it out. It doesn't work. The other way to move in Series B is to multiply by 2. If we look at multiplication, we can see that each time we're multiplying by 2 or doubling. Therefore, we can make this comment about Series B. So Series 2 multiplies by 2 or doubles each time. Doubling is simply another word for multiplying by 2. If it multiplied by 3 every time, we could simply say that it triples. But there's another question that we really want to ask about these. Not simply how do they grow, but we want to know this. So the big question is, what function represents A? In this case, we're really looking at Series A as the problem. We want to know what mathematical expression will actually represent Series A. To do that, we need to figure out a couple of things first. Number one, we need to know what does A represent and what is our variable x going to represent. In this case, A is simply our result, or the number of dots in each value. So in this case, I'm just going to say that A represents the result, or in this case, the dots. X, on the other hand, has to represent our independent variable, the thing we get to pick. Whereas the number of dots is a result of the equation, x is what we get to choose. So we get to choose when we look. We get to choose what time or what cycle we are examining. So x will represent our time value, or the cycle we're on. In this case, 1, 2, 3, 4, or 5. To build the function, what we need to do is figure out what values of x can be combined to get A. So to do this, let's build a T-chart. We'll have x on the left side representing our time values, 1, 2, 3, 4, and 5. And we'll have the function A of x, or our result, on the right-hand side. These results are simply the number of dots. In this case, 2, 4, 6, 8, and 10. So the main question we have to start asking ourselves is, how do we get from our number on the left, 1, to the number on the right, 2? And there are a couple of ways to do it. So let's look at this first couple of values. To get from 1 to 2, you could add 1 or multiply by 2. Either of those will function. To get from 2 to 4, we could try adding 1, which is the same as what's up top, or we can multiply by 2. Very quickly, it becomes apparent that 2 plus 1 is not equal to 4, so addition can be marked out. if we check 3 multiplied by 2 to see if it gives us 6, it does. So we can see that multiplying by 2 is going to be the key factor in building our expression, or our function. So in this case, our function, a of x, is equal to 2 times x. We can take all this information from the T-chart we just built. We have our multiply by 2, and 1, 2, and 3 are simply representations of x. So we put it all together, and we get a of x is equal to 2x. Here for series B, we're asking ourselves the same question. What function represents series B? I've gone ahead and drawn my T-chart, copying out my x values and my b values, or my results, because x and b represent the same things they did for series A. X meaning time, and b meaning the result, or number of dots. So how do we get from 1 to 2, 2 to 4, 3 to 8, and 4 to 16? Well, just like in the last example, we could try adding 1 or multiplying by 2. And very quickly we once again see that addition doesn't work. And once we hit the third value, we can see that multiplication doesn't work, because 3 times 2 is 6, not 8. So now we turn back to the whole purpose of an exponential function. It's another way to increase a value. So our question becomes, what exponent combined with 1 will result in 2? The common thing to jump to immediately is 1 squared, because it's 1, which are our x values, raised to an exponent, but that does not equal 2. So we need to find a different way to do this. Instead of trying to square 1, let's look at putting our exponent as the variable. In this case, something raised to the x power equals 2. We know that x is 1, because it's right here, so what that means is that the something that's missing here, raised to the first power, equals 2. From this, we can assume that 2 raised to the first power is 2. Let's test it out. If we take our values of x's, let's see what happens. 2 raised to the second power equals 4. 2 to the third power is 8. And 2 to the fourth power is 16. So now we've found our expression, and we can put it as such, that the function b of x is equal to 2 to the x power. Remember, it's perfectly okay to have a variable in your exponent at any time. The only thing you can't have are negative exponents. You have to work those out. Now let's look at what happens when we try to evaluate these two functions. We just sort of want to see what exactly happens. So, first of all, let's look at a of x equals 2x, and we want to evaluate a of 50. So a of 50 equals 2x, and basically all we're doing is we're plugging numbers in. So a of 50 equals 2 times 50, so a of 50 is equal to 100. That's a pretty decent number. If you plug in 50, you get double that back. But now let's come over and let's look at b of 50. So once again, b of 50 equals 2 to the x power. And now let's keep plugging in. b of 50 equals 2 to the 50th power. Remember, when you plug this into your calculator, you're going to type in 2, the caret symbol, and then 50. When you do that, you get an odd number. You get that b of 50 equals 1.12 E15. This is the same thing as scientific notation, 1.12 times 10 to the 15th. So you'll notice the same input, the number 50, got us two drastically different outputs. In this case, 100 and 1.12 quadrillion. Obviously, there's a vast difference there. This just goes to show that even though these two formulas are so incredibly similar, they can create drastically different results. The first one gets you just double the amount, whereas the second one gets you a massive amount, so much higher that it's not even really quantifiable. There's not a good way to explain just how big a quadrillion is until you get into things like grains of sand and droplets of water. As we move on, we really want to look at what do these do for us when we graph them. So speaking of the graph, what we really need to do is start in the same place we would for almost any graph, and that's this. Create a T-chart. We want to have some points that we can easily graph. So, for a of x is 2x, I want to look at 0, 1, 2, 3, and 4. For b of x, I'm going to look at those same values, 0, 1, 2, 3, and 4. We've already determined what x of 1, 2, 3, and 4 are for both of these equations when we looked at our previous T-chart. So I'm really only going to have to calculate x of 0 for both values. If I plug 0 in for x, I get 2 times 0, which is 0. If I plug 1 in for x, I get 2 times 1, which is 2, and we can continue on. Over here, we can do the same thing. If I plug 0 in for x, I get 2 raised to the 0 power, which is 1, thanks to our laws of exponents. Plug in 1, 2 raised to the first is 2, then we get 4, 8, and 16. And these points are what we're going to use to build our actual graph. So let's look at doing that. We need to graph it. So let's look at this graph paper. The first thing to note is that our origin is here, not in the dead center or very lower left-hand corner. So always make sure you're looking at your graph paper. Let's take a moment and number our graph using an increment of 1 both on the y and the x-axis. Now that we've added numbers to our graph, we can actually use this to chart our various points. So let's start with a of x being 2x. From our T-chart, we can go ahead and find the actual points that are going to matter to us. At 0, a of x is just that, 0. At the value of 1, a of x is 2. At 2, it's 4, then 6, then 8, then 10. As we go through this, we can use this to create a line. Like so. Now let's look at b of x being 2 to the x. At a value of 0, b of x is 1. At a value of 1, b of x is 2. At 2, b of x is 4. And at 3, b of x is 8. At 4, b of x is actually 16, which is just off the graph. The first thing you'll notice is that 2 of these points line up exactly, but then the rest don't. While a of x equals 2x is a linear function, which is what we've dealt with before, something that's a straight line, the fact is that b of x is something new. B of x is exponential, and it's a curved line. So when we do this, we just have to go as best we can to match the curve. In this case, our curve looks something like this. Obviously, this isn't perfect. A couple of the key points to remember about the differences between a of x, a linear function, and b of x, an exponential, we can start by talking about their slope. If you look at the function a of x, the slope is always a rise of 2, a run of 1. Rise of 2, a run of 1, to give us a slope of 2 over 1. If you look at b of x and pick a couple of points, for example 0 and 1, you see a rise of 1, a run of 1. From 1 to 2 you get a rise of 1, a run of 2. From 2 to 3 you get a rise of 4, a run of 1. And then we get a rise of 8 and a run of 1, for slopes totaling 1, 2, 4, and then 8. So while a linear function such as a of x has a constant slope of 2 over 1, an exponential function does not. The slope of an exponential function changes at every point. That's one of the key differences between a line and a curve, which we see in both exponentials and quadratic functions, which will be coming up next. As we explore these, one of the big questions we always have is, what exactly is exponential in real life? So let's take a look. When we think about exponential functions in real life, there are a lot of good examples, but some of them are a little more interesting than others. One of the first ones that we always look at when we're talking about exponential is simply cell growth. When we're talking about cell growth, it's a classic exponential doubling function. You start with one cell, it splits into two, each of those splits into two more, and we very quickly go from one cell to more. As we move on, there are a couple of other things that we can go ahead and add to the possibilities. The next one is disease. When you think about disease or biohazards, a lot of diseases such as the flu are actually exponential growth because one source can inflict multiple infections on other people. And in fact, one of the really cool things you can think about is that if you're a fan of a show like The Walking Dead or any other zombie movie, all of those zombie shows, the classic zombie infection is actually an exponential function, as one zombie can inflict multiple people with the disease. One of the other great things you can look at when it comes to looking at this kind of growth is very simple. Money. Money is one of the biggest real-life exponential growth problems in existence whenever we're talking about compound interest at a bank. As we look at exponential functions, we're really probably going to do a lot with talking about money and how you can retire early before the age of 65 if you manage your money well. So as we look at all of these exponential functions and what they do, we're going to discover lots and lots of different ways we can apply these to real-world problems as we go through. But the big keys to remember are this. Exponential function is growth and decay. It's stuff getting bigger and smaller on a curved path. Okay? As we look back at exponential graphs, we can remember that our graphs increase drastically from an early stage instead of our slow-growing straight lines. So think about this. As they grow bigger, what happens to the problem? What happens to the numbers or the values involved? And what is it that we can use these for in real-world applications?